A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
I was looking at the satellite imagery from the Chagos archipelago yesterday, and it really drives home that the world changed on March 14th. We're sitting here on March 22nd, just 8 days after the event, and the high-resolution shots of the airfield are still circulating. Today's prompt from Daniel is about the technical and strategic reality of ballistic missile ranges, and he wants us to use that strike on Diego Garcia as our lens. It is one thing to talk about range in a vacuum, but seeing a hardened aircraft hangar in the middle of the Indian Ocean get opened up like a tin can by a missile launched from thousands of kilometers away makes the physics very real, very fast.
It is a massive shift, Korn. I am Herman Poppleberry, and I have been obsessed with the telemetry data coming out of that event. For decades, we talked about certain nations having regional reach, but what we saw on March 14th was a definitive graduation into the intermediate range category. When you look at the math, moving from a missile that can hit a neighbor to one that can hit a deep water base 4,000 kilometers away is not just a linear upgrade, it is an exponential engineering challenge. The physics do not scale gracefully, they fight you every step of the way.
That is what I want to dig into today. We see these acronyms all the time. Short range, medium range, intermediate, and then the big one, intercontinental. But to the average person, a missile is just a missile. Why does the international community get so twitchy when a flight test crosses that 3,000-kilometer line? Why was the strike on Diego Garcia such a specific oh no moment for the Pentagon?
It comes down to the physics of energy and the geography of power. The classifications are generally broken down into 4 buckets, and these are not just labels. They represent massive jumps in technology. You have short-range ballistic missiles, or SRBMs, which travel less than 1,000 kilometers. These are your tactical battlefield weapons, the descendants of the V2. Then you have medium range, or MRBMs, which cover 1,000 to 3,000 kilometers. That is usually enough to cover a specific theater like the Middle East or Western Europe. But then you hit the intermediate range, the IRBMs, which go from 3,000 to 5,500 kilometers. That is what Iran just demonstrated. And finally, anything over 5,500 kilometers is an intercontinental ballistic missile, or ICBM.
Why 5,500? That seems like a very specific, almost arbitrary number to draw the line for global reach. Why not 5,000 or 6,000?
It is actually a relic of the Cold War and the geography of the Northern Hemisphere. 5,500 kilometers is roughly the shortest distance between the northwestern United States. Think Alaska and the Pacific Northwest and the northeastern Soviet Union. If you could fly that far, you were no longer just a regional nuisance, you were a threat to the other superpowers' homeland. So, that number became the legal and technical threshold in treaties like SALT and START for what constitutes a global strategic threat. When you cross that line, you are playing a different game entirely.
So, when Iran hit Diego Garcia, they were clocking in right around 4,000 kilometers. They are officially in the IRBM club now. But you mentioned earlier that this is an exponential challenge. Let us talk about the rocket equation. Most people think if you want to go twice as far, you just add twice as much fuel. I am guessing you are going to tell me that is not how it works.
I would love to tell you it is that simple, but the Tsiolkovsky rocket equation is a cruel mistress. It is the fundamental law that governs everything we are talking about. It tells us that the change in velocity, or delta V, is equal to the exhaust velocity of the engine multiplied by the natural logarithm of the ratio of the initial mass to the final mass. The key word there is logarithm. To get a tiny bit more speed, which you need for that extra range, you have to add a massive amount of fuel. But that fuel has weight, so now you need more fuel just to lift the fuel you just added. It is a logarithmic spiral of weight.
It is a cycle of diminishing returns. You are building a bigger and bigger firecracker just to move a slightly larger pebble.
To go from a 1,000-kilometer range to a 4,000-kilometer range, you do not just quadruple the fuel. You might have to increase the size of the missile by a factor of 10 or more, or drastically improve the efficiency of your engines. This leads us to the concept of the mass fraction. For an ICBM, about 90% of the weight at launch is just propellant. The actual warhead, the re-entry vehicle, and the guidance system might only be 1 or 2% of the total mass. When you move from a medium-range missile to an intermediate-range one, like the one used in the Diego Garcia strike, you are often moving from a single-stage to a two-stage or even a three-stage architecture. You have to shed that empty weight of the first stage fuel tanks as soon as they are empty, or you will never have enough energy to reach those higher velocities.
Let us look at the propulsion then. In our earlier discussions, specifically back in episode 918 when we talked about Iran's arsenal, we focused a lot on the shift from liquid to solid fuel. The Diego Garcia strike used a multi-stage solid propellant system. For the uninitiated, why is solid fuel such a big deal for a long-range missile compared to the old liquid-fueled Scuds we saw in the 90s?
Liquid fuel is high maintenance and strategically risky. You have to fuel the missile right before launch, which can take hours. That makes you incredibly vulnerable to a preemptive strike because a satellite can see you fueling up on the launch pad. Solid fuel is basically a giant stick of specialized rubbery explosive, usually something like hydroxyl-terminated polybutadiene that sits inside the motor casing. You can store it for years, and when you need the launch, you just push a button. It is instant on.
But if it is so much better, why did we ever use liquid fuel?
Because liquid fuel is more efficient. It has a higher specific impulse, which is basically the miles per gallon of the rocket world. Liquid engines can also be throttled, turned off, and restarted. With a solid motor, once you light that candle, it is going until it is gone. Engineering a solid motor that can burn for several minutes without burning through the side of the casing is a massive metallurgical and chemical hurdle. For a 4,000-kilometer flight, you need that motor to be perfect. If there is even a tiny bubble or a microscopic crack in that solid fuel grain, the surface area of the fire increases instantly, the pressure spikes, and the whole thing turns into a very expensive pipe bomb on the launch pad.
So they have the motors down. But range is useless without accuracy. We used to hear that the further a missile goes, the less accurate it gets, because small errors at the start of the flight result in massive misses at the end. If you are off by 1 degree at launch, you might miss by 50 kilometers at the end of a 4,000-kilometer flight. But the reports from Diego Garcia show they hit specific infrastructure, not just the island in general. How did they decouple range from accuracy?
That is one of the biggest misconceptions in modern rocketry. In the old days, you relied entirely on inertial navigation systems, or INS. These are high-end gyroscopes and accelerometers. If your gyro drifted by a fraction of a degree over a 10-minute flight, you would miss by kilometers. But now, we have multi-mode guidance. These missiles are using satellite navigation like GPS or the Russian GLONASS or even the Chinese Beidou system to mid-course correct. They are essentially checking their homework against the satellites every few seconds.
But wait, can we not just jam the GPS? If I'm the United States Navy on Diego Garcia, I am screaming jamming signals at every frequency I can find the second I see a launch.
You can jam it, but the missile is smart. It uses the satellite signal to constantly calibrate its internal gyroscopes during the quiet, high-altitude parts of the flight where jamming cannot reach. By the time it hits the jamming zone near the target, its inertial system is so finely tuned that it can fly the last few dozen kilometers on its own with incredible precision. And for the terminal phase, the part where it actually hits the target, they are likely using optical or radar seekers. The missile has a digital map of the target area in its brain, something called digital scene matching area correlation, and it looks out the window to match what it sees with that map. It is essentially a 4,000-kilometer sniper shot.
That brings us to the most terrifying part of the flight, the re-entry. When you are talking about a 4,000-kilometer range, that missile is not just flying through the air like a plane. It is going into space, reaching an apogee of maybe 800 kilometers, and then screaming back into the atmosphere at hypersonic speeds. I have read that the heat can reach thousands of degrees Celsius. How does the warhead not just vaporize before it hits the ground?
It is a brutal environment. When that reentry vehicle, or RV, hits the atmosphere at Mach 12 or 15, it creates a massive shock wave. The air in front of it gets compressed so violently that it turns into plasma. This does two things. First, it creates a plasma blackout where radio signals cannot get through, so the missile is blind and deaf for a few minutes. Second, the heat flux is high enough to melt almost any metal known to man. If you used a standard steel or aluminum casing, it would be a streak of molten metal in seconds.
So you need some serious material science. What are they using?
They use ablative heat shields, often made of carbon-carbon composites. These are materials designed to char and flake away, carrying the heat with them as they erode. It is a controlled sacrifice. The engineering challenge is making sure the shield wears away evenly. If one side erodes faster than the other, the shape of the RV changes, it starts to tumble, and it burns up. The fact that Iran successfully landed multiple warheads on a small island 4,000 kilometers away tells us their carbon-carbon manufacturing and their vibration testing are far more advanced than many analysts gave them credit for. You cannot just buy this stuff on the open market. You have to build the specialized looms to weave the carbon fiber and the high-pressure ovens to cure it.
It feels like we are seeing a collapse of the technical barriers that used to keep this technology in the hands of just a few nations. If you can build a solid motor that does not explode and a heat shield that does not melt, you are basically 80% of the way to an ICBM.
You are hitting on the strategic anxiety here. The jump from 4,000 kilometers to 5,500 kilometers is mostly just a matter of adding a bit more fuel or a third stage. The hard parts, the guidance, the staging, the reentry, those have already been solved. This is why the strike on March 14th was such a wake-up call. It proved the threshold has been crossed.
Let us talk about the strategic calculus for a minute. Diego Garcia is often called the footprint of freedom in the Indian Ocean. It is where the United States keeps its long-range bombers and massive pre-positioned supply ships. It was always considered a safe haven because it was out of reach of almost everyone's regional missiles. Now, that safety is gone. How does the United States Navy adjust to a world where their deep-water sanctuaries are within the crosshairs of a land-based battery thousands of miles away?
It forces a total rethink of power projection. If your base is vulnerable, you have to spend a massive amount of resources on missile defense, like the Terminal High Altitude Area Defense, or THAAD, or the Aegis system. But as we have discussed in previous episodes, the math of missile defense is punishing. It costs way more to build an interceptor than it does to build the missile it is trying to stop. If a nation can mass produce these IRBMs, they can simply overwhelm the defenses. The strategic depth that the United States relied on in the Indian Ocean has effectively shrunk. You can no longer assume that being 2,000 miles away from a conflict zone makes you safe.
It is the same thing we talked about in episode 9464 regarding the technical audit of their arsenal. The shift to mass production means they are not just building a few boutique missiles for parade days. They are building a magazine. They are building a capacity to saturate a target.
And that brings us to the international monitoring side. How do we stop this? The main tool is the Missile Technology Control Regime, or MTCR. It is an informal association of countries that agree to restrict the export of missiles and related technology capable of carrying a 500-kilogram payload at least 300 kilometers.
300 kilometers? That seems like a very low bar compared to what we are talking about today. Why is the limit so low?
Because 300 kilometers is the threshold where a missile becomes a strategic tool rather than just a tactical one. The idea is to nip it in the bud. If you can stop the export of high-end gyroscopes, specialized resins for carbon fiber, and multi-stage rocket engines, you can slow down the development of these longer-range systems. But the problem we are seeing now is indigenous development. Iran has its own space program. They launch satellites into orbit. And here is the secret. A space launch vehicle and an ICBM are basically cousins.
I was going to ask about that. Every time there is a satellite launch, the State Department puts out a memo saying it is a cover for ICBM development. Is that just political rhetoric, or is the technology truly interchangeable?
It is very interchangeable. To put a satellite in orbit, you need to reach a velocity of about 7.8 kilometers per second. To hit a target on the other side of the planet with an ICBM, you need about 7 kilometers per second. The propulsion is the same, the staging is the same. The only real difference is the guidance software and the fact that an ICBM needs a re-entry vehicle to survive the trip back down, whereas the satellite stays up there. If you can put a 1-ton satellite into low Earth orbit, you can absolutely put a nuclear warhead on a city 5,000 kilometers away. The fairing that protects a satellite during launch is not that different from the shroud that protects a warhead.
So, when we see these countries testing space launch vehicles, we are essentially watching an ICBM test in slow motion.
That is how the intelligence community looks at it. And this is especially concerning now because we are in an era of unconstrained testing. As we discussed in episode 1157, the New START Treaty expired in February of this year, 2026. That was the last major agreement that provided transparency and limits on long-range delivery systems between the United States and Russia. With that guardrail gone, the signal to the rest of the world is that the era of arms control is effectively over. It is a free-for-all. Without inspectors on the ground or shared data, we are back to guessing what is inside those silos.
It feels like the technical genie is out of the bottle. If the physics are well understood and the materials are becoming easier to manufacture, range becomes a commodity. What does this mean for the next decade? If 4,000 kilometers is the new baseline for a regional power, does that mean the 5,500 kilometer ICBM threshold is going to be crossed by 5 or 6 more countries by 2035?
I think that is a very realistic and sobering assessment. The engineering hurdles used to be a gatekeeper. You needed a massive industrial base to handle liquid oxygen or to weave high-grade carbon fiber. But automation and 3D printing are changing that. We are seeing motor casings being wound by robotic arms in facilities that did not exist 5 years ago. The barrier to entry is dropping just as the geopolitical desire for long-range deterrence is rising. We are moving from a world of haves and have-nots to a world where anyone with a decent industrial base can reach out and touch a target on another continent.
Let us look at the practical takeaways for someone trying to make sense of the news. When we see a headline about a new missile test, what are the 3 things we should look for to know if it actually matters?
First, look at the fuel. If it is a solid fuel missile and it is a multi-stage design, that is a huge red flag. It means they are looking for high readiness and long range. Second, look at the apogee, which is the highest point of the flight. If they are testing a missile on a lofted trajectory, meaning it goes very high up but lands relatively close, they are trying to test the re-entry heat shield without actually firing it over a neighbor's house. You can calculate the potential range from that apogee. If it goes 2,000 kilometers up, it can probably go 6,000 kilometers out.
And the third?
The precision. If they are claiming a circular error probable of less than 50 meters at a range of several thousand kilometers, they have mastered terminal guidance. That is the difference between a weapon of terror that you just point at a city and a strategic weapon that can take out a specific radar installation or a command center. It means they have the sensors and the processing power to correct their course in the final seconds of flight.
It is the difference between a blunt instrument and a scalpel. And what we saw at Diego Garcia was definitely a scalpel. It is a strange new world where the middle of the ocean is no longer a hiding place. The physics of the rocket equation have not changed since the 1900s, but our ability to overcome them has accelerated in a way that I think caught a lot of people off guard.
It really has. I find it fascinating and terrifying that the same equations Tsiolkovsky scribbled down in a log cabin in Russia are now being used to redefine the strategic map of the Indian Ocean in 2026. The math is immutable, but the engineering is catching up to our ambitions. We are seeing the death of distance as a defensive strategy.
Well, on that cheery note, I think we have covered the spread from SRBMs to the edge of the ICBM threshold. It is a lot to take in, but understanding these tiers helps us realize that these numbers on a map are not just distances. They are statements of intent. Every kilometer added to a missile's range is a kilometer subtracted from someone else's security.
They really are. Every extra 1,000 kilometers is a country saying, I can touch you, and there is not much you can do to stop it. It is the ultimate form of geopolitical leverage.
Thanks, as always, to our producer, Hilbert Flemingtop, for keeping the gears turning behind the scenes. And a big thanks to Modal for providing the GPU credits that power this show and our research. This has been My Weird Prompts. If you are finding these deep dives useful, the best thing you can do is leave us a review on your podcast app. It genuinely helps us reach more people who want to get past the headlines and into the actual substance of these topics.
We will be back next time with whatever Daniel throws our way.
See you then. And
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow